Hello friends, I welcome you in lecture number 4 on residues. In this lecture we are going to discuss one more formula for residue at poles. So we consider this result. Suppose that two functions p and q are analytic at a point z0, and second condition is value of function p at z0 is non-zero and function q has a 0 of order 1 at z0. That means value of function q at z0 is 0, but value of first derivative of q at z0 is non-zero. Then the quotient pz over qz has a pole of order 1 at z0, and residue of pz over qz at z0 is given by value of function p at z0 divided by first derivative of q at z0. So if we have this type of function pz over qz, and if we want to decide the residue of this function at some point, then suppose we want to determine the residue of this function at point z0, then two conditions are required to use this result. First requirement is both the functions p and q must be analytic at z0. Second requirement is value of function p at z0 is non-zero and value of function q at z0 is 0, but value of q dash at z0 is non-zero. That means qz has a simple 0 at z0. So if these two conditions are satisfied, then we can decide the residue of pz over qz at z equal to z0 using this formula: value of function p at z0 divided by value of first derivative of q at z0. So we will remember these two conditions. Two conditions to apply this result are functions p and q must be analytic at a point z0. Second requirement is value of function p at z0 is non-zero and z0 is a 0 of order 1 of function q. Then this z0 is a simple pole of this function, and residue at z0 is given by value of function p at z0 divided by value of first derivative of q at z0. So we consider this example. Determine the poles of the function cot z and residue at each pole. So first we write cot z as a quotient of two functions. We know that cos z over sin z is nothing but cot z. So we denote this cos z by p of z and sin z by q of z. So we mention that where this p of z is nothing but cosine z and q of z equal to sin z. So first we have to determine the isolated singular points of this function cot z. So we know that cot z is not analytic at all those points at which sin z is 0. So sin z is 0 if z is integral multiple of pi, that is z equal to n pi, n belongs to z. So we can see that z equal to n pi are isolated singular points of function cot z. So first we write clearly z equal to n pi, n belongs to z are isolated singular points of f of z. So now we have to decide whether z equal to n pi are poles or not, and if they are poles, what will be the order of poles. So there are infinite number of isolated singular points which we have represented in a single expression as z equal to n pi, n belongs to z. Now first we check value of this. Before that we can see that these two functions pz and qz are analytic everywhere, so both are analytic at z equal to n pi. So first condition is satisfied, pz and qz are analytic at z equal to n pi, because cos z and sin z are entire functions, they are analytic everywhere, therefore they are analytic at z equal to n pi. Now first we decide the value of function p at z equal to n pi. So function pz is nothing but cos z, so p of n pi equal to cos n pi, which is minus 1 to the power n, and this is non-zero for each n. So value of function p at n pi is non-zero. Now we find out value of function q at n pi. Function q is sine function, so sin n pi, which is 0 for every integer n, and we require first derivative of q. Qz is sin z, so derivative of sin z is cos z, and therefore value of q dash at z equal to n pi, this is again cos n pi, which is nothing but minus 1 raised to n, and this is non-zero for every integer n. So both the conditions are satisfied. Functions pz and qz are analytic at z equal to n pi. P of n pi is non-zero, q of n pi is 0, and q dash n pi is non-zero. So that means z equal to n pi is a 0 of first order of function qz. So therefore by above result which we have discussed, we can say that therefore z equal to n pi, n belongs to z. Here we have to write these are zeros because there are infinite number of values here. So therefore z equal to n pi, n belongs to z are pole of order 1 or simple poles of function pz over qz, which is nothing but cot z, and we use that formula to calculate residue of pz over qz at z equal to n pi. We have to remember this formula. This is equal to value of function p at n pi divided by value of function q dash at n pi. Now value of function p at n pi is minus 1 raised to n, and value of function q at n pi is also minus 1 raised to n. So we have minus 1 raised to n divided by minus 1 raised to n, which is nothing but 1. So residue at every point z equal to n pi is 1, where n is any integer. So in this way we can use this result to decide the residue at simple poles. We consider one more example. Show that residue of the function tan hyperbolic z over z square equal to minus 4 over pi square at z equal to pi I divided by 2. So here we are given particular point, so we will discuss at this point only. So before that we consider here our function is tan hyperbolic z over z square. So we take first we consider f of z equal to given function tan hyperbolic z over z square, and as we know tan hyperbolic z is nothing but sin hyperbolic z divided by cos hyperbolic z. So we have z square times cos hyperbolic z, and now we consider numerator as function pz. So pz is sin hyperbolic z, qz is z square cos hyperbolic z, and we are interested in the residue at z equal to pi I by 2. So we know that these two functions pz and qz are analytic everywhere, they are entire functions. So first condition is clearly satisfied. Clearly pz and qz are analytic at z equal to pi I divided by 2. Now we find out value of function p at pi I divided by 2. So this is nothing but sine hyperbolic pi I divided by 2. Here we put z equal to pi I divided by 2. Now to find out this value, we remember that relationship between hyperbolic and trigonometric function. If we have sine hyperbolic iy, then it is equal to I sine y. So using this result, here instead of y we have pi by 2. So this is equal to I sine pi by 2, and because sine pi by 2 is 1, we have I. So value of function p at pi I by 2 is I, and it is non-zero. Now we find out value of function q at pi I by 2. So function q is nothing but z square cos hyperbolic z. So we put z equal to pi I by 2, z square, that is pi I by 2 square cos hyperbolic pi I by 2. So this is going to be pi square I square divided by 4, and here we have cos pi by 2, because we know this relationship between hyperbolic cosine and trigonometric cosine. Cos hyperbolic iy is nothing but cos y. Here y equal to pi by 2, and cos pi by 2 is 0. So that means value of function q at pi I by 2 is 0. Now we check the value of functions q's derivative at pi I by 2. So for that we first find out derivative of q. Function q is z square cos hyperbolic z. So here we have to apply product rule. Z square as it is, derivative of cos hyperbolic z is sine hyperbolic z. Cos hyperbolic z as it is, derivative of z square is 2z. So using product rule we find out derivative of function q. Now we are interested in the derivative's value at pi I by 2. So q dash pi I by 2 is going to be pi I by 2 whole square sine hyperbolic pi I divided by 2. Here 2 times pi I by 2 and cos hyperbolic pi I divided by 2. Now this is nothing but pi square I square divided by 4, and as we have discussed, sine hyperbolic pi I by 2 equal to I sine pi by 2. Here we have 2 will cancel out, and cos hyperbolic pi I by 2 equal to cos pi by 2, but cos pi by 2 is 0, so that term is going to be 0, and here I square is minus 1, and we have pi square I divided by 4, because sine pi by 2 is 1, I square is minus 1, so we have minus pi square I divided by 4, which is non-zero. So value of q dash at pi by 2 is non-zero, and value of q at pi by 2 is 0. That means qz has a simple 0 at z equal to pi I by 2. So both the conditions of that result are satisfied. Pz and qz are analytic at z equal to pi I by 2. value of function p at pi I by 2 is non-zero, and qz has a simple 0 at z equal to pi I by 2. So therefore pz over qz has a simple pole at z equal to pi I by 2, and residue of pz over qz at z equal to pi I by 2, this is given by value of function p at pi I by 2 divided by value of function q dash at pi I by 2. Now value of function p at pi I by 2 is nothing but I. So first we put value of function p at pi I by 2, which is I, and value of q dash at pi I by 2 is minus pi square into I by 4. So minus pi square into I divided by 4. So we can see here I will cancel out, and this we can rewrite as minus 4 divided by pi square. So therefore pz upon qz is f of z at z equal to pi I by 2 equal to minus 4 by pi square, and f of z is nothing but tan hyperbolic z over z square. So therefore residue of tan hyperbolic z over z square at z equal to pi I by 2 is nothing but minus 4 divided by pi square. So we are asked to prove this, that residue is minus 4 by pi square. So using this standard result, we are able to prove this residue of this function equal to minus 4 by pi square. So in this lecture we have used this result, that if we have quotient of two functions pz and qz, then two conditions are required to calculate residue at z0. First condition is both the functions are analytic at z0. Second condition is value of function p at z0 is non-zero, and z0 is a 0 of order 1 of function q, that is q of z0 is 0 and q dash z0 is non-zero. And if these two conditions are satisfied, then residue of pz over qz at z0 is given by value of function p at z0 divided by value of q dash at z0, which is non-zero. So this is all about today's session. I hope you like this lecture. Thank you very much.